So this talk is from me and Galina. So we are both senior engineer in the R&D center. We work on the voice assistant. And basically the theme of the talk will be synthetic dialogue generation. So first of all, I want to say from the beginning that this talk will be on a tool called SDialog, which was not created by us. It was created by a team led by Sergio Bodiso in the IDIAP Research Institute in Switzerland. And so it is actually an academic work. So we use an open source tool, and then we have modified it to make it able to allow us to work with data for XPENG. And so it is kind of an example of academic industry collaboration. We have talked with Sergio and with the team from IDIAP a couple of times. And so we have exchanged ideas and everything. So we have not like a long-term collaboration, but we have some communication. So basically, let's start with the R&D center here in Munich and basically explain what we do. So the reason we have a team here in Munich for the voice assistants is very simple. We need people who can work with localization, who understand cultural expectations and norms in Europe, people who have some language competency with European languages, and then we need it for GDPR compliance, because some of our work is to work with user data, do some analysis, some business intelligence, and this is something that cannot be done from China. But a big part of the work that we do is working on the actual models, not for training them, but for evaluating them. So to first start, I would like to give like a very, very simple introduction on some kind of evolution for voice assistants. So there used to be a classic model for voice assistant, which was very, very modular. So it would start here basically with some voice recognition. The audio would become text. It would be sent to the natural language understanding. The natural language understanding then connects with the dialogue manager. The dialogue manager would activate the functions that would need it to be activated in the car. Then it would launch some TTS, some pre-recorded TTS. And that was all very nice and simple and very modular. And the thing is that starting basically from 2023, I would say, there was the introduction of large language models. So this introduced a lot of changes. First change is the introduction of language generation. So there is not only language understanding, but language generation. So the assistant is able to respond and to respond in a way that is particular to exactly what has been said by the user. So this introduces a lot of complexity in the dialogue that can be created, because you can bounce back and forth between a user and the assistant for an arbitrary amount of time. And you need multi-turn conversations that maintain context memory, so memory of what has happened earlier in the conversation. Another big change was the introduction of multimodal models. And so you have lots of different models, speech-to-speech model, all kinds of models. And basically now you have models that work directly with audio. So the audio is now directly in contact with the language understanding, which means that you also use the audio to understand the intent of the user. You don't discard the audio right after the speech recognition. So all of this leads to some omni models, they are called now. So models that are able to do everything, models that are multimodal, multilingual as well. Because especially here, for example, we need to deal with different languages. And so you have models that can recognize audio, text, maybe even video. You have some chit-chat tools where the user is just speaking for speaking. You have some tool calls where you actually need to launch some response. And then you have context memory for long conversations. So ideally, when you work with voice assistants, you would like to use online data, or user data actually is easier to understand, because user data is basically the golden truth. So you know what the users want, how they say it, how they want it. The problem is that when you work for a Chinese company, things have to move fast. And so you cannot wait to launch some feature and then hope to get some feedback. And then in 3 months, you optimize your feature. So before a feature is launched, you have no data. After it is launched, you have a little bit of data, but if you are looking for edge cases, you might look for a long time. And then once you have data, you still to annotate it. So the annotation might introduce some noise. You might have different languages. You need lots of people. It is slow. Introduce some errors. And so basically the solution that we have found is to work with synthetic generation. So we generate data, and especially the important part is we generate data that is pre-annotated. So we generate structured data, pre-annotated data, so data that is complex, but still that we can work with without having, or with having minimally human intervention. So now we'll talk a little bit about the voice interface inside the car. And first, I will introduce the SDialog model and paper. So the SDialog is the paper that was published in 2025. So like I said, by Sergio Bodiso and his colleagues. And the point of SDialog is basically to use LLM generation to create structured data. And so at the center of the SDialog is the concept of personas, which are basically virtual people, kind of simulated by the computer, to talk between themselves and with the voice assistant. Then you have some agents. So you have LLM models that you call to generate natural language. You have different ways of doing that. You can have different agents for different people, and then they bounce back and forth. Or you can describe all the people and then send it at once to an LLM to generate a full conversation. But basically, the object at the center of SDialog is the dialogue object. So this dialogue object contains all the turns, so all the different utterances, all the labels, all the metadata, all the tool calls, all the persona, all the annotations. Everything is contained in this object. This object is for text dialogues. It is then sent to an audio pipeline to work with TTS to create audio data. And the SDialog paper also contains a section about evaluation. So how to evaluate the dialogue that you have created on different metrics, so linguistic diversity, accuracy of the annotations, model comparison between different models, and so on and so forth. So all of this is used and already exists inside the model. And then once you have like a dialogue and you know basically how it is going to run, then you can actually also work or like directly work, make some modifications in real time in the dialogue. And you do this with what they call orchestrators. So for example, you can start a dialogue, and then at some point you would like the user to change their mind. They wanted to buy this, now they want to buy that. And you would like use some orchestrator to introduce this variability inside the dialogue. So this is the model as it existed, and now this is what we are doing with it. So first, the building blocks, which are personas and situations. So personas are simply simulated people, and it is a structured object where you can basically add everything that you want. So for us, we have added things like an age, gender, what they do in life, what is their personality, what is their native dialect, the way they speak. And so this persona is used to generate the text data because people have a way to speak, like the way they choose their words and everything, but it is then also used for the audio. And so the persona is for the people, the situation is for all the context around the conversation. So you might be a person in a car, they might be in the US, maybe the traffic is bad, there is some storm, and then they want to go to some destination, and there is some noise, both inside and outside the car, and Galina will talk about this more later. And here we come to the major, I would say, block that we have added to SDialog, which is we have created a way to pre-annotate the data into SDialog. So SDialog was a tool to create freestyle data and then try to inject tool calls inside of this data. And we have done the opposite. We have pre-created the tool calls, and then from the tool calls, we create the conversation. And so, for example, we might pre-create a skeleton of a dialogue, which will contain, for example, a tool. So we know this person wants to go somewhere, and then an argument. He wants to go to IKEA Westfield. The assistant will reply with some kind of list containing all the possible destinations, and the user will then choose. And so all of this kind of like weird looking kind of code will be sent to the LLM, and will become natural text. So it will become something like, hey, can you navigate to IKEA Westfield? Sure, I will set up navigation. One destination was found, and then the user chooses to the destination. So we have different types of logic for different domains. Here is like a selection of domains. We have more domains. So we have navigation for when user want to go somewhere, car control, to use the different tools inside the car, chit chat for just free chats, car condition when the user wants to know what is happening inside the car, and some custom domains. We have actually plenty of these. So now to give you an overview of the way this works, or the way that this dialogue structure is created, I will introduce these 5 concepts. So first you start from a tool. So every turn in a dialogue is usually associated with a tool, even if it's just chit chat. The tool will tell you what the user wants to do. This tool will be ordered into a sequence that is called a play. And a play is ordered through some rules. So different tools can come one after the others, but there are rules. These plays will then be transformed into a dialogue template that will give you exactly the number of turns and who is speaking, and the arguments will be populated. So we'll have arguments kind of like waiting to be populated. They will be populated here. It will be sent to generate a dialogue, and the dialogue will be sent to generate some audio. Here's an example of how you create a play. So different domains have different strategies. Here we have some state machine. So basically for navigation, you will be in different states. So you start in a state of no navigation, and you will ask for some destination, and you might get 0 response, in which case the dialogue is already over. You might get a single response, and then you will choose your route, how do you want to go there? Or you might get several responses, and then you will first select which one is the correct one, then how to go there. Then you will be in a state of active navigation. Then you can ask many questions. You can add waypoints. You can ask about something on the map. You can refresh the route. You can ask when you get at your destination. And at some point, you will either cancel navigation or get to your destination, and you will go back to a state of no navigation. So basically for these navigation dialogues, every turn will contain the stage directions with the state, what the turn is doing, how many results you get, and what is the most probable next step, next tool. So we need some structure to organize the sequence of tools. We also need some structure to organize the context that is kept inside of the dialogue. And so, for example, for navigation, we have, for example, some context, which is the destination. So it will be created during the play creation and then inserted into every subsequent play. So every time you can either refer to the context immediately or more in the distant future. And for the domains, so for the domain like car control, you will have more complicated domain context situations. So you might have a function that you first open and then close. You might have a function that you set to some value and then change it. You have a function that you set to some position here for the driver, then change for the passenger. You might be in some position and open some function, then open a different function. And basically the way this works is that during a play, all the possible context carrying situations are predetermined. So you know if you can use the context or not. And then according to some probability, the context might be used or might not be used. And so if the context is used, it will be saved in the turn context, so the turn object. Then it will be sent to the LLM instruction in the prompt. And then the LLM will be forced to use some deictic reference to some previous term. The LLM will have to say, use that function or do it now. So they will use this or that or it or now. And this way we can force it to generate situations with different context that is passed to different dialogues. Then we can insert chit chat or other function inside of this, but this logic stays the same, and the information is carried forward during the play. And so basically here is a little bit of summary. You start with a personal situation. You decide on a domain. You will create some play. The play will define the tools and the arguments, but the arguments will be abstract. Then you will create a dialogue template where you will know exactly how many turns you will have and in what order and how they are going to happen. Then you will fill all the arguments. So you will know, for example, that you will have the POI arguments. And then at this stage, the POI will be filled. So it will be, for example, you're going to go to McDonald's. And for the rest of the conversation, the destination will be McDonald's, unless you change the destination. And finally, this is sent to LLM generation. And so we have simplified this with some recipe config. So every dialogue has a recipe which contains its personas, its situation, and its place. All of this is passed all the way to the LLM generation. And at this point, the text dialogue is created with all its metadata and all its annotations. And then that's where the text part goes into the audio, and the audio is Galina.
So now we have the text dialogue from the text generation step. We have the predefined labels, which we generated beforehand, and we have all the metadata we need. So the dialogue is generated for the persona and the situation that we need. Now, what we need is the audio, and that's what our tool is doing as well. So our goal is to generate the audio that sound exactly like the person that we described in the beginning for the situation that we described in the beginning of the generation of the dialogue. And those are two steps. So first is voice synthesis, and the second one is acoustic simulation. So for the first step, originally what we did was to use the standard TTS approach, like Microsoft, Kokoro, Google Cloud, or in-house. And it's good, it's very clean. We can have high quality voices with natural prosody. Sometimes we even can have the emotional instructions for some TTS, and for sure we have reliable and stable output. Yeah, but there are some drawbacks. And for our specific use case, because we need to evaluate our models, the main drawbacks is it's too perfect. So there are no accents, there are no dialects, and there are obviously no speech defects. And also what we need is more diversity in our data. So we need some hesitations, we need some different pause styles, and so on. So the standard TTS is too perfect. They have also predefined voices. Of course, they are too good, but we need more diversity in terms of speakers as well. And another problem is we do not have any voice customization, so we cannot create new personas based on our description. That's why we moved to the other step, where we tried to use the voice cloning approach. So as probably you know, the voice cloning allows us to use the sample of the audio and the text to generate the audio that sounds exactly as our sample. And this is good because it allows us to have the consistent multi-turn conversation with the same voice. Also, it can be highly personalized, right? Because we can select the people, we can select the personas and the voice. But the drawback here is that it requires large, clean recording per voice. And also, the quality depends heavily on the voice bank quality. So first of all, what we need to do is to create the voice bank, so to collect a lot of data of the voices. And actually, that's the problem here in Germany. So we cannot easily collect the data of the people. And that's not a lot of high quality open data sources. So that's why we moved to the third option, which is the persona-driven approach. And the first model that we tried is the family of the Qwen 3 TTS models, basically voice design and base model, which allow us, first of all, to generate new voices for new persona based on a free-form text prompt using the voice design model. It supports multilingual personas. And finally, we have the approach where we can generate personas on the fly based on the persona description from the beginning. But the drawback here is that actually the quality varies significantly because it's a free-form text prompt, and we cannot rely on these results if we generate this on the fly. So sometimes the model can just forget that we asked to generate it for some specific dialect or accent. And that was the main problem for us. So not actually predictable. Then also the problem was that in order to run this, we need to run it on the fly. We need to have two models at the same time because we need to use voice design to generate the persona and then to use the base model to clone the voice. which means 2 services on the same time. And it also requires a lot of prompt engineering for consistency to develop how we should define the personas. It is free-form text, but still it is a prompt. And that's why we move to the last option, which we actually are using right now. It is a K2 FSA model. It is TTS from Caldi of the 2nd generation. And the benefit here is that actually, first of all, it supports different accents for English, which sounds really natural. It supports different dialects for Chinese, almost 12, I think, for Chinese. Again, it is high quality output, and we can generate data using only one model, both to create the new persona on the fly and also to do voice cloning. And that means that we can actually generate the personas on the fly using only one service, which is good. The problem here is that it has slightly less flexibility in terms of persona description because it's not free-form text prompt. They have different characteristics like age, accent, pitch characteristics for the voice, but we still can use it to create our voice bank. And that's actually what we do right now. So even though we can generate the personas on the fly, but most reliable approach would be to pre-generate some voice bank and still use it, because then we can at least check if the accent is correct, if the dialect is correct, if everything is sufficient for us. And that's what we're using right now. So we have the voice bank of the personas based on some description. If we do, we can use it using the voice cloning approach to generate our dialogue. But if we, for example, do not have this persona or there are some specific characteristics, we can still generate this person on the fly. Good. Then we need to simulate the acoustic. So when we are in the car, we, for example, have the driver who is speaking to the voice assistant, but imagine you have children playing on the back seat, you have dashboard fans, also outside there is some traffic, some sirens and some horns, and we need to simulate this scenario in terms of, and again, in terms of acoustics. So first of all, we need to identify where these sources of noise are located. And using these locations, we can simulate this scenario. Usually in standard signal processing, people are using this formula. So we already have the clean TTS output. And let's assume we have the characteristics of the room. In our case, it is car cabin. So we can generate room input responses, 1 and 2, for different sources of the noise. We can use it then to mix it all up into the final mix of the voice and noises, which are located in a specific location, like outside of the car, inside of the car, and everything. And generally, what people do in research groups, they define the characteristics of the room, like 3D geometry, some absorption coefficients for the materials that we have inside the room. Then we place some sources of the noise in different locations of this room. And using, for example, Pyroom Acoustics Library, which is open source, we can emulate the characteristics of the room for this specific location of the noise. Then we use these generated room impulse responses to have the mix of, to make the sound, to make our speech sound like it's coming from this room in this location. Then we can mix it with the background noises, and voila, we have what we require. But what we found out during our experiments that unfortunately Pyroom Acoustics has some simplifications. And our car cabin is not so simple. It's not just sandbox, it has different materials inside. So it's complicated to define this geometry carefully. And also we have people inside, and people also have their own absorption coefficients. So the sound actually doesn't seem so natural in this scenario. And that's why what we are using right now is the real room impulse responses that we recorded in our cars in 4 different locations. Lucky for us, the majority of the sounds are in these 4 locations. So the driver position, the front passenger position, and the back seats. Also, what we did, we collected the pre-recorded real noises, and the majority of these noises is the constant noises. So like fan or like traffic, which is happening outside, like road vibrations, which are specific for the car movement. This is also our modification. But we also work not with only just normal noises like traffic, we have some specific acoustic scenarios. And for example, like passengers who are chatting on the back seat, or like I said, children who are playing. We can have siren, which has the Doppler effect, which going from far closer to our car. All these kind of scenarios we can try to simulate using the standard signal processing approach. Like for chatting, for example, we can just overlap with different samples of the voice. For the siren, okay, we can simulate this using the standard approaches, and also Doppler effect. We know how it works, like we know the physics. But sometimes there are more complex situations which we also should think about. And for these situations, we aiming to use the generative approach. So what we are trying to do now is to use some generative model to generate the noise, and later then to use this for augmentation. Well, basically that's it. Let's start with the technical details. Let's jump directly into the demo. Let's see how this works. So what we did specifically for this event was we add some user interface for our tool. And in this tool, I can go and I can predefine which LLM I will use, which temperature. I can select any of two languages right now, English and Chinese. I can specify the domain which Florent was talking about, so what will be the dialogue about. And then let's go to the user persona. So I can select any kind of the persona that we pre-generated before, so our voice bank with some characteristics. I will go with Sunita because this is my favorite one. Sunita is 68 years old. She's a retired physician, and she lives in Melbourne, driving to the community center and family visits, right? So she's patient in conversations, and this is a characteristics of her personality, but these characteristics affect mainly the text dialogue. So how she chooses the words, how she generates her dialogue, this case. What is more important for the audio is that she has Indian English dialect, accent, sorry. Then I will go for the characteristics for the assistant persona, and I will go just with Aria, our female voice. With American English, I can define the situation, let's say shopping, etc., and augmentation. So for augmentation, I can choose any of different kind of noises, but I will go with a fan, like AC noise, on the medium level. Then I can generate text, I can generate audio, I can run the full generation. I did it beforehand, so we can see here the example. This is the text, the results of the text generation step. We have different turns for Sunita and for our car assistant Aria. We also have the details of the screen response, so basically what Sunita will see on her screen inside the car, and the details about the labels, so the tool name, the arguments, and so on. Here you can see this small chat, but let's jump into the audio and maybe, so we can also have the clean audio, the result of the TTS. I will just show you the augmented one directly. I hope we are sharing the sound.
Take me to 423 Oak Street, downtown. I found matching locations for this address. Please select one from the list on the screen. I pick the first one. First location selected. Estimated travel time to your destination is 18 minutes. At a stop at the large clothing boutique on our current route, your waypoint has been added and the route is updated to include it. Search for home goods stores along this driving route. I found several home goods stores along your route. Please select one from the screen. The first result works for me. The first POI is selected. Now please choose which route you'd like to take from the options displayed. End this current navigation session. Navigation has been canceled.
Okay, so this was one example. We also have the possibility to export all the files, just in case you would like to test it further. We also have the debug, because this is actually the interface, and we have both the user interface and API commands, so we can also do that and see what are the details of these API requests. Well, it is running, it is alive still, and we can test it more, probably maybe after I will finish with the presentation, but we have more and more really interesting personalities which we can check. We have Russian accents, we have Korean accents and everything. But you see, that's what we now do after our daily job, just play with personalities. So now I would like to talk about how we actually use this tool, because all this user interface is nice, but it doesn't make sense to use it. What we do in our everyday basis is we use this tool to generate more and more different data, different dialogues with different personas, situation, some different noises, etc. And then we use this inside our evaluation tool, which allow us to test our voice assistant on these dialogues. We have different metrics. We also have the possibility to run LLM as a judge, and also we test the functionality correctness for our voice assistant. Then what we do, we diagnose the results, we compare the models, we find out if there are some bad cases. That's actually our main responsibility, to find these bad cases and to break the model of voice assistant. And then when we found out what are the bad cases, we can refine the place, we can modify our training data, retrain the model, and do another iteration of the whole loop. That's basically what we do. So we also have several next steps how we would like to improve our tool. And the first step is to add another layer on top of this tool and to be able to define the dialogues using our natural language description instead of predefined components. Then the next step would be to integrate it with our user data analysis tool. So that's the task that we also have. We all the time analyzing the real data of the real users. Yes, so it would be really nice to connect one with another, and then, for example, found some bad case in our user data, and then tell our tool, yeah, generate me more like this. I need more. And voila, we will have our bad cases to test our models. The last next step is to use the annotation tool. So what we have right now, even though we predefine initially, we predefine initially the situation and the persona, so we know the tool and the arguments. Sometimes it can happen that during the generation process, the label should have been modified. And in order to work with this carefully, we need actually to verify the labels after that. For that, we can use the annotation tool, which will do this automatically. And we already are working on that. That's basically it. And that's all. I just would like to finish with a citation of the original paper of the guys from IDEAP, that SDialog reduces fragmentation in research workflows and enables controlled, reproducible experimentation with LLM-based conversational agents. And that's actually exactly what we do here now in production.